All right, last time we talked about the lambda calculus and about how it is a core, very simple language that includes all the interesting things that computations can do, and how it can represent via functions and object-oriented encoding things like numbers, booleans, pairs, and so on. And at the end, we talked about how it can simulate recursion via this thing called the fixed point operator. Now, one thing that you may not have realized before is that when we introduced lambdas into our language and removed top-level functions, we actually lost recursion. So it used to be that we could write functions like this. We could write factorial, where we wrote if equals n0, 1, otherwise times n fac minus n1. Close the fac, close the times, close the if, close the define. So we can write this function and it worked totally fine. But if we tried to write the same function with lambdas, it wouldn't work. So fac5, for instance, that was fine in J2, I believe is the language. But in J3, if we tried to write this, we could write let fac equal lambda n if equals n0, totally fine, 1 times n fac n minus 1. Okay, so we could try to write this, but we're going to get an error that's going to say that that fac right there is unbound. And it's unbound for the same reason it's unbound in the lambda calculus. Now, because our language J3 includes all the lambda calculus, that means that we could write this with the z combinator. We could write that and that's totally fine. In fact, what you should do, I think it's task like 35 or something like that, is to implement a lambda calculus version of fac in your language, in your J2 language, sorry, in your J3 language. But what we want to do is we want to make things more convenient and more efficient. So what we're going to do is we're going to change our language. We're going to go from J3 to J4. And we're going to make a very small change to the language. It used to be in J3 that the syntax for lambda was lambda x dot 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 e. And we're going to change that. So in J4, the syntax is going to be this, lambda x dot 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 e. Where this name right here is a recursive name. So it's the name for the lambda itself. And so we could write this, for instance, by naming this ifac, that's for inner fac, and then putting that ifac. And now it is a J4 program. Okay, so that's the change that we're making to our language. Basically what it does is it allows us to have recursive functions that can see themselves. Now, here's the way that we can write down the semantics for this. We would say that E of L v0 through vn, where L is equal to lambda f x0 through xn e, that's going to be equal to E of the body, that E, where we're going to go in and we're going to find F and replace it with L. Then we're going to find x0, replace that with v0, and so on till we get to vxn replaced with vn. Okay, so this is a very simple rule. We then need to change the CK machine to deal with it as well. So the CK machine is going to change in the following way. We're going to add a rule that says lambda f x dot 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 e, that's for the body, and an environment, k, is now going to go to something new. So it's going to go to a closure. Let's write that as just C. So a closure named C. And it's going to have an empty environment, and the continuation is going to be K. where C is going to be equal to a closure with lambda f x dot 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 E and environment prime. Notice that it's environment prime, not environment. Where environment prime is environment, but it has been extended with one thing. It's been extended with a mapping from F to the closure C. So the idea here is that now the closure that we made has a reference back to itself inside of its environment. So now it is recursive. Okay, now how could we realize this rule right here in our in like your C implementation, for instance? Sorry. Well, what we would do is we'd have something like this. So in your C code, you're going to be switching on the type of the C value. And you're going to have a case for lambda. And in that case for your lambda, what you're going to do is you're going to make a new environment. So I'm going to call it environment P. That's for environment prime. I'm going to call my function makeEnvironment that constructs a new environment. And it starts with the old one, and then it has a pointer to the function of the lambda. And then it has a null. Okay. Then what I'm going to do is I'm going to set C equal to making a new closure with the code and the new environment. I don't know why I said that, the function there. It's going to have a pointer to the lambda. So that's just C. Oh, sorry, and that's why I did it. I'm saying that cfun is the name of the recursive name. So C, let's call it rec name. I like that better. Rec name. So that's the recursively available name. Okay, so then the closure has C in the environment P. Then what I'm going to do is I'm going to go into environment P, and I'm going to change the value, that null right there, to point to C. Then what I'll do is I'll set the environment equal to null, and then I'll break. And then I'll be done with that case for lambda. And so this is what my rule for lambdas looks like. I construct the new environment, I make the closure, I make it so that the environment is cyclic, and then I'm moving on. Okay, now one thing that I highly recommend that you do, though, is you should add a rule in your desugarer to make it so that you don't have to actually write down it all the time, right? Your desugarer is going to have a rule that looks something like this. You're going to say, when you desugar and you give me lambda, and then you give me a list of variables, x0 through xn, and then some body expression, you're going to turn that into an actual lambda. And I'll use the symbol lambda. This is your old rule. Your old rule is going to say that it's going to go to lambda x0 dot 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 xn through desugar eb. Okay, that's what your old rule is. Let me move this around for a second. Okay, your old rule. Now your new rule, what it's going to do is it's going to say it's going to turn it into something like rec x0 through xn desugar eb. Okay, and then you're going to add another case for your desugarer where you allow the user to actually write down something. We'll call that f. And then we'll have x0 through xn eb. And so this is going to equal lambda f x0 through xn g sugar EB. Okay? So the idea here is that if you don't use a recursive name, then one gets generated for you, and it's just rec. Otherwise, you can specify your own. Now, once we have recursion like this, we can start building lots of useful functions. Like, for example, we can build functions that do things a number of times. So, for example, we could write a function called nat unfold fzn that looks like this. If n is equal to 0, then return z. Otherwise, call f on n and nat unfold fz sub 1n. So basically what this thing does, nat unfold, basically calls a function f times on z, kind of like how the lambda calculus works. Here's another one that we can write, do times, where we'll have some variable x, and then we'll have some exit condition, and then the answer value, and then the increment, and then the body code. So this right here is something that we'd put in our desugarer, and it would turn into something like this. It would turn into let last equal EC, so we'll compute when the last thing happens. Then what we'll do is we'll have a lambda called repeat that's going to take as one argument x, and another argument the answer. So those are these two variables. Then we're going to say if x is less than the last, then what we'll do is we'll call repeat, that's this function, with a new x plus 1, and then we'll take this code right here and put that in, and then otherwise we'll return the answer, and we'll close off that, and then we'll start this off with 0 and ed. So for instance, here's how we could use this. We would write something like do times, and we could write, we'll have it be I, and it's going to go until it gets to 5, let's say. And then we'll call the answer sum, maybe. And then we'll have the initial answer be 0. And then we'll have the code be something like I plus sum. Okay? And so what that's going to do is it's going to turn into, via our desugarer, let last equals 5 in lambda repeat I sum. And then where it's going to say if I is less than last, then what we're going to do is we're going to call repeat on I plus 1 and I plus sum. And then otherwise, we're going to return the sum, and we're going to start off it as 0 and 0. Okay? So what this does is it's going to start with I being 0, sum being 0, and it's going to keep incrementing I and making the sum get larger and larger until we've summed up the numbers 0, 1, 2, 3, and 4. Okay, so this is basically like a little It's basically like a little for loop. This is an example of what you might call a macro, where we have some pattern in our desugarer that actually expands into something quite complicated. We're going to start seeing more of these because our language, J3, has become so advanced. There's very little features that we need inside of it that are not already there, and so we can implement many things inside of the desugarer. I think that's actually pretty much all we need to do for today. I guess today is a little bit of a shorter content, so I'll see you next time and we'll learn about a new thing.